Welcome to this short unit on nuclear chemistry. We'll do a little nuclear after we talk about atomic structure, and specifically now in the nuclear chemistry unit, we'll look at how elements formed in the first place and how we're looking at forming new elements, some synthetic elements. We'll also talk about what makes elements and atoms stable and why it's kind of difficult to just synthesize any new element. It seems like it should be a piece of cake. Throw some protons, neutrons, electrons together and boom, I got a new atom. Maybe not quite so simple. The beginning of this study guide has a very adorable little, kind of comic that talks about how elements were formed. We'll go through some of that together in class, but it might be helpful just to read through that little comic and have some background on how elements originally formed. In general, here's kind of a summary. There is this theory called the Big Bang Theory. And like we mentioned earlier, theories are things that seem to make sense with the data available at the time. So with all of the data we know today, this Big Bang Theory has some credit to it. Now, talk to me in 10, 20 years, and we may have to adjust this theory. Obviously, we think then that there was some kind of an explosion many years ago. Temperatures were very high, all matter was kind of annihilated, and we only had forms of energy. But as the universe expanded and cooled, some of that energy was condensed into protons, neutrons, and electrons. As the universe continued to cool, then some of these protons, neutrons, electrons condensed and formed the early elements, hydrogen and helium, some of the most simple elements. Hydrogen being just one proton and one electron, because the atomic mass of hydrogen is about 1. So most hydrogen atoms don't even have neutrons. And then the next simplest element, helium. Helium has 2 protons, 2 electrons, and 2 neutrons, with a mass of 4. Okay, so we've got these early elements, simple atoms like hydrogen and helium. Well, as hydrogen and helium condense, we can have nuclear fusion reactions. Fusion is where you take smaller nuclei and join them together. You fuse them together to start making larger elements and larger atoms. This diagram is kind of nice. So remember from atomic structure, when we see these nuclear symbols, the number on the top, that's the mass. And on the bottom, that's the atomic number. Or in other words, the number of protons. So let's say I have 2 atoms of helium. They're in the same place at the same time, and they just happen to unite in this massive collision of nuclei. We can join 2 helium atoms and form a beryllium. And look what happens. So the mass of each helium is 4. The mass of the beryllium is 8. We join all of the protons and the neutrons from the helium nuclei, and they're still present in the beryllium nuclei. The 2 helium atoms each had 2 protons, so beryllium has 4. Atomic number 4 on the periodic table. What do you know? Beryllium. And this goofy little symbol here, this stands for energy, which we'll look at further in some of the next couple videos. And then you can see how this cycle continues. Now what if I have a beryllium atom and it collides with another helium atom? Boom, we form carbon. We have an atomic mass of 4 plus an atomic mass of 8, which gives us atomic mass 12. And then down on the bottom, helium had 2 protons, beryllium had 4. Carbon has 6 protons. On the periodic table, element number 6 is carbon. And so on. These little nuclear fusion reactions are responsible for a lot of the smaller elements, up to iron. Nuclear fusion reactions. in the sun and the stars are responsible for a lot of elements up through iron on the periodic table. Now after that, some of the heavier elements were formed from different kinds of nuclear reactions, which we will look at in the next few videos. And as you get down toward the bottom of the periodic table, there are many elements that are synthetic, that were formed in these particle accelerators. We'll also look at particle accelerators in class more. It's these giant tracks where we just spin atoms crazy high speeds and basically try to collide them together and hope that particles stick, that I form enough protons and neutrons so that the resulting particle is somewhat stable. And again, some of these higher elements, heavier elements, and different kinds of nuclear reactions we will look at further in the next few videos. In general, then, most stable nuclei have a number of neutrons equal to or greater than the number of protons. Okay, most stable nuclei. The number of neutrons is at least the same as the number of protons. We also mentioned isotopes when we were talking about atomic structure. Most elements do exist in isotopes where they have certain versions of the same element. They have the same protons, they have the same number of electrons, but they do have varying numbers of neutrons. Now some of them are more stable than others. And so if we kind of look at isotopes, and especially the most stable isotopes, we get a plot called the band of stability. We're going to look at graphing the number of neutrons in these stable isotopes versus the number of protons. And we get some kind of interesting trends when we look at this graph, this band of stability. The plot or the graph will show that lighter atoms or lighter isotopes are most stable when that proton-neutron ratio is really close to 1:1. Smaller atoms are pretty stable when we have a proton-neutron ratio of 1:1. This will cover about the first 20 elements, but the first 20 protons. But now as you get more than 20 protons, beyond element number 20, calcium, then we see some changes occur. Now we did kind of mention too in the last chapter when we were talking atomic structure that the nucleus is positive. It contains positive protons and neutral neutrons. But as you get more and more positive protons, these like charges do repel. You're trying to shove a whole bunch of positive protons in this condensed nucleus, and there will be some repulsion. Well, to try to alleviate that repulsion, we need neutrons. They're like the peacemakers of the nucleus. But as we get more and more protons, it seems like above 20 protons, we do need more than a 1:1 ratio of protons and neutrons to make that nucleus stable. We're trying to avoid that proton-proton repulsion in the nucleus. 20 seems like the magic number. After element 20, we need some extra neutrons. There's too many positive protons. We're going to need extra neutral neutrons to try to avoid that repulsion of the positive protons. So as you get some of these bigger atoms, the proton-neutron ratio can be over 2:1. And that's kind of the trick when trying to synthesize new elements. It's really hard to figure out the perfect number of neutrons to make this nucleus stick together. You know, as I get more and more positive protons, there's more and more repulsion. That's what's tricky about making new elements. We have to find the perfect number of neutrons to form a somewhat stable nucleus. Now it does mention down here that atoms greater than 83 protons and masses greater than 209 are really never considered stable A lot of these are radioactive, which means it's a nucleus that's unstable and tends to decay, which really means that it just like splits and forms smaller particles that are more stable. And again, a lot of these are synthetic. And if they're synthetic, they're often not stable. Here's the band of stability. Check it out. Oh my gosh, it's life-changing, isn't it? I guess. So here's the band of stability. We have number of neutrons plotted against number of protons. There we go. And so it kind of makes sense that this straight line in here, this line represents a 1-to-1 ratio of protons to neutrons. Well, way down at the bottom, the smaller atoms really do kind of follow that trend. And look at this little guy down here. Magnesium. Magnesium is element number 12, 12 protons. His mass is really close to 24. Now, again, we mentioned in the last chapter when we talked about isotopes, if I look at magnesium's mass on the periodic table, it's about 24.3. So yes, there are some isotopes of magnesium that are heavier, but the most stable and the most abundant magnesium atoms really do have a mass of about 24 AMUs. It's a perfect 1-to-1 ratio of protons and neutrons. If the mass is 24 and the atomic number is 12, we have 12 positive protons and 12 neutral neutrons, no charge. That pattern seems to fit for the small atoms until you get about element 20. So here we're close to 20. They've got potassium on the chart. Potassium is number 19. If I look on the periodic table, its mass is really close to 39.098. Or here, this is just an alternative isotope of potassium. But all potassium atoms really do have a mass close to 40, somewhere between like 39 and 41. So they're fitting in this band of stability. They're kind of following this trend. We're up until about 20 protons, element number 20. We do have stable atoms with about a 1-to-1 ratio of protons to neutrons. But look what happens then as you get bigger nuclei. This band dictates from our line that represents the 1-to-1 ratio of protons to neutrons. So here is the band of stability. It does not follow the trend, and in fact it tends to favor more neutrons than a 1-to-1 ratio. Now what's kind of interesting about this chart is that we could predict new elements. For example, if I look at the very bottom of the carbon family, some periodic tables will have a box for element 114. Element 114 should be below lead. Now the periodic table I'm looking at right now has a box that mentions element 114 as a possibility, but it doesn't really have much data on 114. It doesn't have a name even. Check out this periodic table, or this graph here. Let's say I try to estimate 114. Alright, so here would be element 110. Let's put 114, I mean it's somewhere in this box, of 110 to 120. Let's follow it up. So I'm estimating a little bit. What kind of make it up that high? And then what if we kind of extrapolate this band of stability? So the band of stability would keep going. We could kind of estimate an approximate number of neutrons that would make element 114 stable. If we keep following this up, And then what if we follow it over? Somewhere around 180 neutrons would be needed to make element 114 stable. A little more than 180 neutrons, which is more than a 1-to-1 ratio. So scientists can use this trend, a graph of these elements and their stable numbers of protons and neutrons, to predict how many neutrons might be required to make a new nucleus stable. Element 114, the carbon family elements are very stable. Carbon, silicon, tin, lead, we'll look at some of those in class. They're very stable. So I don't know, I have a feeling that element 114 could be stable someday. If we can figure out how to synthesize atoms with 114 protons and somewhere a little over 180 neutrons. That's how we can use this band of stability to predict how many neutrons are required to make a particular atom stable.